video is called Calibrating Time. Now I'm really excited about making this video because I believe it's going to solidify my position that Planck's constant is a quantum of energy, and Planck's energy equation is the equation of 1 second's worth of energy units. In 2016, the Perimeter Institute for Theoretical Physics had a conference on time called Time in Cosmology. This was a week-long conference from June 27th, 2016 to June 30th, 2016, and I tried to get into this conference. I believe that I had a really good grasp of what time is. Basically, what I wanted to do was I wanted to go there and talk about time in terms of change. So as you may know, and I've said many times, time is an emergent property of change. And so the aim of the conference was to discuss the key questions in early cosmology in light of the question of whether time is fundamental or emergent. And of course, I believe that time is emergent, but it is also fundamental. Change is fundamental, time is emergent, but in the context of change, time is fundamental. So I wanted to go to this conference and have discussions with intelligent people about this idea. But they did not let me come to this conference. This was an internal conference only, and even though I am a member of a university community, they did not let me come to this conference. I asked Lee Smolin personally, sent him an email, and practically begged him to let me come to this conference. I was actually able to go to a conference on black holes in a previous year. I think that was in 2013. And so I really thought I had a chance that they would let me come to this conference, but they didn't let me come. So that was fine. That was fine. It was a long shot anyways, and so I was good with that. That same year, I had already published a paper called Calibrating the Universe and Why We Need to Do It. It was published in a journal called Physics Essays. This is a Canadian journal, an international journal dedicated to fundamental questions in physics. And actually this was, I was trying to use this, the fact that I'd published this paper, to try to get into the conference at the Perimeter Institute, but I was unsuccessful. But I was successful at passing peer review and getting this paper published in Physics Essays. So here is the abstract for that paper. In this paper, this is where I officially start talking about Planck's constant in terms of a quantum of energy. I place the time variable into the equation as specified by Juliana Brooks. And I also talk about the quantum of mass in this paper, which is Planck's constant divided by c squared, and the quantum of momentum, which I talk about which I have in my specification. And so this was the first official paper. I had written another paper on this talked about this a little bit in a previous paper called The Mandelbrot Set and the Fractal Nature of Light, the Universe, and Everything, which I presented at a conference called SPIE, and that was in 2013, I believe. I presented that paper and the Mandelbrot set paper. And so this paper was sort of an extension of that. And so this paper was more of my official first stab at defining modified unit analysis. In fact, this paper is the first time I actually coined the term modified unit analysis. So in my Calibrating the Universe paper, I refer to dimensional analysis as domain analysis. And the reason I do this is because the word dimension has many dimensions. It's an ambiguous term because the word dimension is used to talk about the dimensions of space, the 3 dimensions of space, and in mainstream, time, space, mass, and charge are referred to as dimensions. And so I call it domain analysis. This is the domain of time, the domain of space, the domain of mass, and the domain of charge. And so these are the base domains of the system. And the system is the universe. The system is cosmology. The system is physics. Okay, so these are the domains, the root domains, the base domains of the system that we are calibrating. So these are the domains of the system that I calibrated in my paper. And so I would say that the domain of space has 3 dimensions. So instead of saying the dimension of space has 3 dimensions, I say the domain of space has 3 dimensions, and that removes the ambiguity from the language. But today we're going to be focusing on the domain of time. Okay, we're going to be calibrating the domain of time. And of course, in the standard systems of measurement, in all the standard systems of measurement, the unit of time is the second. And of course, the second has been redefined over time. So the second was formerly defined as 1/86,400th of the mean solar day. That was the original second. Later on, it was redefined based on the year, on this year, 1900. But in 1967, okay, in 1967, the second was provisionally defined as the second as 9,192,631,770 cycles of the radiation associated with the transition between the 2 hyperfine levels of the ground state of cesium-133. So this is the atomic clock, and this is why I put that little message up in my community section. I wanted you to look at the experiment that they do, the setup that they use to define the second. So the second again is 9,192,631,770 cycles of emission of a cesium atom. And so you can look up the article that I posted in my community section. This is the actual setup. This is the actual setup. And this is a schematic of the setup. And they have a nice video that shows how they calibrate to the second. Now, this is exact. The second has actually been calibrated to exactly this many cycles of the cesium atom. And in the experiment, if you read that website, you would find that it has been calibrated, that the temperature is almost absolute 0 in this experiment. So temperature matters in this experiment. At almost absolute 0, the cesium atom oscillates this many times exactly. And so the second has been calibrated to exactly this many cycles. And so this is nice because this gives us a reference for the second. So when I say 1 second in standard units, I'm talking about 9,192,631,770 oscillations of the cesium atom. So this is how mainstream calibrates the second, how they calibrate the unit of time. The unit of time in SI units, in the SI system, in the standard system, is this number here, 9,192,631,770 cycles of the cesium atom is 1 tick of the clock, 1 second. And so this is nice. This is a good reference. I will be referencing this when what I'm going to be doing in this video is I'm going to be recalibrating, and I'm going to be defining different units of time. So instead of 1 second being this many oscillations, instead of the unit time being this number of oscillations, I'm going to change the number of cesium oscillations that are associated with unit time. I'm going to shrink unit time basically. And you're going to see something really interesting happen when I do this. But before we recalibrate time, before we redefine the unit of time, I'm going to show you what happens when you redefine any of the reference units from different systems. And so in the SI system, where there's two systems that are more commonly in use. There's the SI system, and then there's the CGS system. Now the CGS, C stands for centimeter, G stands for gram, and S stands for second. So both systems have the second. Time is the same, the unit of time is the same for both the SI system and the CGS system. What changes is the domain of space and the domain of mass. And so in the CGS system, the unit of space is centimeter, and the unit of mass is the gram. Okay, and in the SI system, obviously the unit of space is the meter, and the unit of mass is the kilogram. So what this does is it changes the numbers that we plug into our equations. It changes the numbers for the constants that we plug into our equations. So what you have to do in this case is you have to scale the constants. You have to scale the constants of nature when you have a different system. So between the SI system and the CGS system, the unit of time, there's a one-to-one relationship. So the second, the unit of time, is the same for both of these systems. The unit of space, however, in the SI system, the unit of space is 100 times bigger than the unit of space in the CGS system. And the unit of mass is 1,000 times bigger than the unit of mass in the CGS system. And so with this knowledge, then we can rescale the constants using this information. For example, the speed of light in the SI system, in the standard system, is 299,792,458 meters per second. But in the CGS system, the speed of light is this number. It's 100 times bigger. It's 100 times bigger because the ratio of centimeter to meter is 100 to 1, or meter to centimeter is 100 to 1. And so we have to multiply this by 100 to get the speed of light in terms of centimeters per second. And so let me see, what is this? 1, 2, 3, 4, 5. So it's 29,979,245,800 centimeters per second. So when you change the systems, when you modify the systems, when you modify the units of the systems, you have to rescale all of the constants of nature. So here we rescaled the speed of light, and here I'm going to show you how you rescale Planck's constant. Now in the SI system, Planck's constant is reported as 6.626 e to the minus 34. So this is 6.626 times 10 to the minus 34. And in the CGS system, Planck's constant is reported at 6.626 times 10 to the minus 27. So this it is 7 orders of magnitude bigger. This is number is actually bigger than this number, because when you have to the 10 to the minus, right, this is actually a smaller number than this. So this is 7 orders of magnitude bigger than this number. So to understand why this is 7 orders of magnitude bigger than this number, we look at the units. Okay, so the units of Planck's constant in standard units, I'm just going to do standard units now, not modified unit analysis, are the kilogram, meters squared per second squared times S. And in the CGS system, it is grams times centimeters squared per second squared times S. Now in the SI system and the CGS system, both have the second. Okay, so they both have the same second, which is calibrated to the cesium atom. So we don't need to scale the unit of time. but we do need to scale the unit of space and the unit of mass because both of them are different in these two systems. And so let's do the mass first because so we have a kilogram here and a gram here. There's a 1,000 to 1 ratio between a kilogram and the gram. So there's 3 orders of magnitude right there. And the unit of space is 2 orders of magnitude. So the meter is 2 orders of magnitude bigger than the centimeter. So there's 2 orders of magnitude, so that's 5. But if you notice here, the meter and the centimeter are squared. And so 2 squared is 4. So we've got 4 orders of magnitude here, 3 orders of magnitude here, leaving us with a 7 orders of magnitude difference between these two systems for Planck's constant. So that's pretty straightforward. That's easy. Hopefully that's easy to see. This is how you scale Planck's constant from the CGS system to the SI system and vice versa. So now what we're going to do is we're going to redefine the unit of time. Previously, we only scaled the domain of mass and the domain of space. So now we're going to scale the domain of time. We're going to rescale the unit of time, and then we're going to recalibrate all of the constants of nature, at least the important ones that we need for this discussion. We're going to rescale them using this new unit of time. So in the SI system, 1 second, the unit of time is equal to 9,192,631,770 cycles of the cesium atom. So when you count this many cycles, that equals to exactly 1 second. Now I'm going to define another system. I'm going to call it S2. This is going to be called S1. So the unit of time in the SI system, I'm going to call S1. And the unit of time in the S2 system, I'm going to call S2. So in the S2 system, I'm going to define the unit of time as 919,263,177 cycles of the cesium atom. So that is 10 times less cycles than in the SI system. So we could easily recalibrate time to any time scale we want. Okay, it hasn't been done historically, but if we wanted to, if we had justification for it, we could define the unit of time as this many cesium atom cycles. And so when you do that, you have to rescale all the constants of nature. So here we're going to be scaling the speed of light between the SI system and the S2 system. Okay, so in the SI system, which is this many cesium clock ticks of the cesium atom, the light propagates at 299,792,458 meters per unit time. And so in the SI system, the unit time is the standard second that we know and love, that we've always had. And so this is the distance that light travels in this many cesium atom ticks. Now in the S2 system, which is 919,263,177 cesium ticks, so an order of magnitude less cesium ticks, light propagates at 29,979,245.8 meters per unit time. Okay, so the meter didn't change, the unit of space didn't change, the meter didn't change, so this is still in meters, the meters that we know and love, but now this is per new unit time. I redefine the unit time to be this many ticks of the cesium clock. Therefore, a light pulse will propagate this distance, so the speed of light is not slowing down. This is a smaller number because light travels a different distance in the new unit time. So hopefully that makes sense. Hopefully you can see that, because if you don't get this, you're not going to get the rest of what I'm doing. And so, so this is what happens to the speed of light. The numbers change. The numbers that we plug into our equations change depending on which system you are in. So for the sake of completeness, now I'm going to scale momentum. I'm going to scale the concept of momentum. And so in the previous slide, I showed you that there was a 10-to-1 scaling of velocity between the S1 system and the S2 system. And so you can see here are the units of momentum. The units of momentum are kilogram meter per unit time, kilogram meter per unit time. The unit times are different in these two systems. So to scale momentum, so you notice there is the kilogram is not, mass is not scaled. There's a one-to-one relationship between the mass in these two systems. There's a one-to-one relationship between the spatial domain in these two systems. The meter is the same. The only thing that changes is the unit of time. And so you can see that this is a velocity term. So the scaling of momentum is going to be the same as velocity. There's going to be a 10-to-1 scaling between these two systems. So if I am in this system and I'm running experiments and I get my numbers out, but I want to scale back to the SI system, then I would multiply my answer by 10. So now we're going to scale energy. We're going to scale the units of energy. And so if if I'm running an experiment and the answer is in terms of energy, and I want to scale back to the SI system, I need to know what that scaling factor is. And so you'll see here, so there's a 1-to-1 ratio between the units of mass, so I don't scale that. There's a 1-to-1 ratio between the units of space, the meter, and so I don't scale that. I only need to scale the time component. And so the velocity had a 10-to-1 scaling factor, the momentum had a 10-to-1 scaling factor, and this is because the S was not squared. In the energy, the units of energy, S is squared, the unit of time is squared, and so you have to square the scaling factor. And so to convert from energy from this system, the S2 to S1, if I get an answer in terms of energy, I have to multiply it by 100 to get back to the SI units. If I calculate an energy in SI units, I have to divide by 100 to get it in terms of the S2 system. Okay, so now we need to scale Planck's constant. How do we scale Planck's constant? And this is where it gets a little tricky. This is where the problem comes in. This is where the bug, I call the bug, can be found. Okay, so first I'm gonna do it the way mainstream does it, and I'm gonna show you what I get, and then I'm going to do it my way, and I'm gonna show you what I get. And so here you can see that, so I divided the action constant. Okay, I separated it into two just to distinguish between the units of energy, because we know the energy scales is 100-to-1. We know that energy scales 100-to-1, and the unit of time has been scaled 10-to-1. And so, so what to do with this extra S? This is the problem. What do we do with this extra S? Okay, historically, what they do is they take this unit of time and they cancel it with this unit of time. Okay, they do this. And so now what we have is, these are the units of angular momentum, apparently, allegedly, the units of angular momentum. And so this is what in mainstream would try to scale. And so what happened here was we had to scale 100-to-1. Okay, we had to scale 100-to-1 because this was squared, but now we scale 10-to-1 because we canceled one of the s's in this term and wrote the units of Planck's constant as the units of angular momentum. And this is how it's historically done. And so if mainstream had their way, they would scale Planck's constant this way. And so the Planck's constant in the S2 system is 1 order of magnitude smaller than in this system. And so to convert Planck's constant from this system to this system, we divide by 10. And to convert Planck's constant from this system to this system, we multiply by 10. So now we're going to apply Planck's energy equation to these two systems. And so here are the two Planck's constant in the SI system and Planck's constant in the S2 system. And I'm going to choose an arbitrary frequency of 10 to the 7. So this is 1 with 7 zeros. 1, 0, 0, 0, 0, 0, 0, 0. That would be 10 million cycles per unit time. Okay, so and the speed of light in the system is 2.99, etc., times 10 to the 8 meters per unit time. And the wavelength of this frequency is 29.97 meters per cycle. Okay, so this is a fairly large wavelength. This is in the order of the short wave. This would be a short wave wavelength of electromagnetic energy. And when you plug the frequency and Planck's constant into this equation, you get an energy of 6.626 times 10 to the minus 27 joules. And this is the joule of the S1 system. This is the joule from the S1 system. So now we redefined the unit of time to be 919,263,177 ticks of the cesium atom clock. And so I'm using the same light source. Okay, my light source oscillates 10 to the 7 times per standard second. So it oscillates 10 to the 7 times in this number of cesium atom ticks. And so obviously and logically, if I am counting light clock ticks, okay, if I'm counting light clock ticks in the new system, I'm going to get 10 times less clock ticks in this unit time. Okay, so my new frequency in my new system is going to be 10 to the 6. So that's 1,000,000 cycles per unit time, my new unit time. And so I'm getting 10 times less as many ticks in unit time because my unit time is 10 times shorter than the standard time. Okay, the speed of light is also an order of magnitude smaller than in the SI system because in unit time, light propagates 2.99, etc., times 10 to the 7 meters per new unit time. Okay, this is the new speed of light. This is the new frequency. This is the number of light clock ticks per cesium clock ticks, if you want to put it that way. And so when you take the speed of light and divide it by frequency, the new speed of light, and divide it by the frequency, you get the same wavelength as before, which is great because we did not scale the meter. The meter is the same in these two systems. So if the wavelength worked out to a different number, then I did something wrong. But the wavelength doesn't work out to a different number, and so this system is correct. So now we're going to calculate the energy using this equation. And so when you do that, when you plug in this frequency and this Planck's constant, you get 6.626 times 10 to the minus 29 times 10 to the minus 29. And then if you multiply that by 100 to scale the energy back to the SI system, you get the same number as you got before, 6.626 times 10 to the minus 27. And so, so what does that tell us? It could tell us two things. It could be telling us that, yes, this is the energy of a photon, because I get the same number. Or it could be telling us, yes, this is the energy collected in unit time. So this is the energy collected in unit time in this system. And when you convert this energy back to here, you're getting the unit time in the number of pulses, number of energy pulses collected in unit time here. So this doesn't actually help me separate out who is right. Is this the energy of a photon, or is this the energy of 1 second worth of oscillations of my light source, of my one atom that is emitting light continuously over unit time? And so it's good that I get the right answer when I scale back to here, but it's also not good because I still can't tell who is right. So here's the thing. It's my opinion that this operation where we cancel this S1 with this S1 and this S2 with this S2, that this is not the right thing to do. And I'm going to explain why. Okay, so this is the way mainstream does it. And this bothers me. So in mainstream, so you got this equation, E equals Planck's constant times frequency with units kilograms, meters per second squared, times second, times the units of frequency. And so historically what was done was this second is canceled with this second, okay, and you end up with meters squared per s to the power of 1 instead of s to the power of 2. And this just doesn't look right to me. It doesn't feel right. So, but this is how it's done. And so it's and they've been working with this for, 100 years or so. And so it's not completely wrong, but there is something wrong with it. And so I'm going to move on. And what I'm going to do is I'm going to apply the same logic to the momentum equation of quantum mechanics. And so the momentum equation of quantum mechanics is momentum equals Planck's constant divided by wavelength, which when you convert to the frequency domain, you get Planck's constant divided by the speed of light. And the units for this equation are the units of momentum times that extra s from the Planck's constant times the frequency term. Now in this case, and this is how it's done in practice, in this case what they do is they cancel these two units of unit time. They cancel these two units of time, reference time, and so now this constant, the Planck's constant divided by the speed of light, is missing reference time. Okay, here is a constant. In modified unit analysis, this constant is the quantum of momentum. Okay, in modified unit analysis, this constant is the quantum of momentum. But in standard units, this constant has units kilogram times meter. And we've lost reference time altogether in this constant. Reference time cancels. You've got no reference time in this constant, which is analogous to Planck's constant. It's analogous to Planck's constant, only it's lost reference time. So this is a constant associated with a momentum, but there's no reference time in there. There's no reference time in there. This bothers me. This doesn't look right to me. I'm a computer scientist, and this is a system. And I design systems, I build systems, I'm technically a systems analyst, I analyze the systems I build, and if I saw something like this in someone else's system, I would circle it with a red marker. I would say red flag, red flag. Okay, so this doesn't look right to me. And so here is something I found. When you go to the NIST standard, when you go to the NIST standard, this value, 2.10219, etc., times 10 to the minus 42, which is the same number in my constant, 2.10219, etc., times 10 to the minus 42, has units of kg. Has units of kg. Okay, so, but I just did it here. It actually has units of kilogram times meter. In the standard, this is the standard units. This isn't even modified unit analysis. This constant has units kg, kilogram, meter. Okay, kilogram times meter. And so what they do, so for some reason they rate the kg, but they don't rate the meter. And here's what they do. Here's what they do. And this really bothers me. Okay, so what they do is they admit that this is the value, Planck's constant divided by the speed of light. It is exactly the right value for Planck's constant divided by the speed of light. But here they are multiplying the inverse meter. They multiply the inverse meter to the constant. Okay, they are multiplying a unit to a constant to get rid of that annoying meter, which they don't know what to do with it. I'm pretty sure that's why they did this, because they don't know what kilogram times meter is. It's not a standard unit. It's not a derived unit. It's not really anything that is useful. In fact, this is junk. This is nothing. This is completely meaningless, in my opinion. Okay, so they refer to it as the inverse meter kilogram relationship. They multiply this constant, which has units kilogram times meter in the standard system, and then they multiply it by inverse meter to make the meter disappear, and they give this value the unit of kg. You give it the units of mass. There is so much wrong with this. I can't even begin to express how wrong I believe this is. You don't multiply a constant by unit. You can't multiply a constant by unit. You just can't do that. But here it is. They're doing it right here. And that's not the only place they do it. They also do it with the constant h times c. Okay, they do it with the constant h times c, and they call it the inverse meter joule relationship. And they also do it, they have an inverse meter Kelvin relationship where they're multiplying a constant by a unit. Okay, there's definitely something wrong here. And my gut tells me there's something wrong. My instinct tells me there's something wrong. My system analysis background tells me that there is something terribly wrong with this. And if there's something wrong with this, then there's something wrong with this. And so I do it differently, and I'm going to go through the logic of how I would prefer that this is done, and I'm going to hopefully show you that my way is more logical and more meaningful than what they are doing here.